Hey everyone, I am Ms. Hu, your physics teacher. In this video lesson, we're going to compare and contrast series and parallel circuits in terms of current, potential difference, and resistance. So the prerequisite to understanding this lesson is that you have to know what current, potential difference, and resistance are. If you don't know what they are, please watch my videos on those respective electrical quantities. I'll put the link to those videos in the description below for current, potential difference, and resistance. By now you should know what an electrical circuit is and how to set one up. We're going to go straight into the comparison of these physical quantities in the electrical circuits. But before we get there, of course, we all know Ms. Hu's slides are not complete without a meme. So if you were to compare serial and parallel killers, that's an electricity joke. So now let's get to it. So this slide is blank because I'm going to draw this out. So yes, you're going to bear with my drawing, and we're going to go step by step into understanding the comparison between current, potential difference, and resistance between series and parallel circuits. And for this, let's put two resistors in both the series and parallel circuits. So for the series circuit, this is the cell. And say we put two resistors in series with each other. Now, these resistors do not have to be identical. The resistors can have different resistance values. So here in the series circuit, we have two resistors, and in the parallel circuit, we have two resistors. Now, these resistors do not have to be identical. They can have different values. So I'm just going to label them as R1 and R2. So let's assume, for the sake of comparison, that the R1 in both circuits are identical and the R2 in both circuits are identical, but R1 and R2 are not necessarily identical. So here's what we're going to do. We're going to compare the current that's flowing through R1 and R2, as well as the current that's flowing out from the power supply and into the power supply. Alternatively, you can also put an ammeter here. Let's say we put A1 and A2. Okay, that's terrible drawing, but you know what I mean. We're going to just compare I1, I2, I3, and I4. So you have to remember, in a series circuit, the current that's flowing through the circuit are exactly the same from beginning to end. Remember that current is the rate of flow of charge. So it's not how much charge that's flowing, it's how much charge per second that's flowing through a point in that circuit. A lot of students make the mistaken assumption that current decreases as it flows through parts with resistance. So a lot of students think that, oh, when current flows first, I3, when it gets through R1 and comes out at I2, it gets lesser, and out through R2, as it comes out the other side, it decreases even more. That's not true. Remember that we're talking about the flow rate over here. So if there's only one path, then the current has to flow at the same rate. So if you say current at I3 is more than I4, that means that there's a lot of current flowing initially, and then there's less current at the end. Now think in real life, what if that were to happen? There's going to be a traffic jam, right? There's going to be a lot of current backup. So if we were to liken the current against water flow, we're saying that if we say I3 is more than I4, that means there's a high rate of water flow here and it decreases as it flows. But if that were to happen, that means there's traffic jam, there's a blockage at one point, and that causes the entire circuit to slow down at the same time. You have to remember, in electron world, there's no traffic jam. The electrons are smart enough. They're not smart, but they know how to adjust. If one part of the circuit was to slow down, the entire circuit will slow down as well. So I'm going to write here in the current cell that I1 is equal to I2, it's equal to I3 equals to I4. Now, for the parallel circuit, let's say current flowing through the R1 line is I1 and the current that's flowing through R2 is I2. Again, you can also put an ammeter here, let's say A1, A2, but I'm just going to put I1 and I2 with the arrow here. I know it's terrible drawing, bear with me. And we're also going to compare the current that's flowing out of the power supply, we'll put it as I3, and the current that's flowing into the power supply, I4. Now for the parallel circuit, it's different because there are branches, right? You can see that current flows out from the cell. When it gets to this junction here, it's going to split into two branches. And then after that, when it comes back to the other side, it's going to rejoin at this junction before flowing back into the terminal. So taking your understanding of current, you should be able to see very clearly that I3, which is the start of the current, is equal to the sum of I1 and I2, and this has to be equal to I4. So always remember, in a circuit, whether series or parallel, however much current you start with, that's how much current you have to end up with. So even for the parallel, how much you start with, it may split, but when it joins back together, you'll end up with the same magnitude of current when it flows back into the cell or the power supply. Now, let's look at potential difference. So now we're going to compare the potential difference across R1 and R2. So for this, I'm going to put respective voltmeters across the resistors. So we have V1 across R1 and V2 across R2. We're going to do the same thing for the parallel circuits as well. V1 across R1 and V2 across R2. We're also going to put a voltmeter to measure the terminal potential difference across the entire circuit. I'm just going to label that as a general V. Now let's recall what potential difference is. Potential difference is the work done to move one unit charge between 2 points in a circuit. So when you look at the series circuit, you can see here that V1 and V2 are across different parts of the circuit. So V1 is measuring the work done to move a unit charge from this point to this point, and V2 is from this point to this point. So when you look at V is the terminal potential difference. It's measuring the work done from this point all the way through V1 and V2 and back to this point. So for a series circuit, V is equal to V1 plus V2. So V is the sum of V1 and V2. Very logical. The parallel circuits is what usually gets most students confused. So if you look at a parallel circuit here, similarly, we have V starting from the front of the terminal here. So it's a work done to move one unit charge from this point through the entire circuit and out to the other side. The difference here though is that the charge has an option between different branches to flow. So it's possible for the charge to flow from here through R1 and back, or it can flow through R2 and back. So you have to look at the flow of current. Because the current has an option to flow between two different lines, if you look at it that way, see here, it flows through R1 this way or R2, you'll find that V1 and V2 for this parallel circuit are actually equal. That's because the way the charge flows. So some students get confused. To understand this better, you can think of it this way. V is the work done per unit charge. And in electron world, they're also very fair. So when the charges flow, when it gets to this branch, to decide how to distribute the charges, it will depend on the work done. You cannot have a situation where more work is done in one path compared to the other path. So to make it fair, both paths must do the same amount of work. That's why in a parallel section, the potential difference is the same. Now take note, this is only true for a parallel section. It's not for the entire circuit. It just so happens that it's true for this circuit because this circuit is made up of only this pair of parallel resistors. If you have a more complex circuit, then the terminal potential difference is not equal to the parallel section of the circuit. So remember, true only for that parallel section. Now, let's look at resistance. So in this case, we're talking about the effective resistance. So if you want to calculate the total effective resistance, meaning the effect that the resistance has on the circuit, how do we get that total? So assuming that the effective resistance, which I'll write as R, so let's say the effective resistance is capital R. So for a series circuit, again, very straightforward. To calculate the total effective resistance, you just need to take the sum of the resistance values. For a parallel circuit, it's not so straightforward. You'd have to use this equation where 1 over R equals 1 over R1 plus 1 over R2. Now before we move on, let me show you why the equation for the effective resistance calculation is like this for the parallel circuit. Now we have already established that V equals V1 equals to V2. We know that I3 is equal to I1 plus I2. For the sake of comparison, I'm just going to make this as I. Let's assume that I is a current that's flowing out and into the cell. From the equation V equals IR, we know that I is equal to V over R. So let's substitute that into the equation. So if I represents a current that's flowing through the entire circuit, we can calculate it using V over R, where V is the potential difference for the entire circuit, or the terminal potential difference, and R is effective resistance for the entire circuit. Now I1 is a current that's flowing through R1. So in order to calculate that, we will zoom in only at R1. So the potential difference across R1 is V1, and of course the resistance is R1. Same thing for I2, we'll look at the potential difference across R2 only, because that's the current flowing through R2. So that's V2 divided by R2. Now we know that V equals V1 equals to V2. So you can actually cut this straight away. In case you can't see how you can cut it, I'm going to do this step by step. So we're going to substitute all the values of V, V1 and V2 with, well, V. So this becomes V over R1 plus V over R2. Taking V out as a factor, you'll have V over R equals to V 1 over R1 plus 1 over R2. So now you can cut V, leaving the equation 1 over R equals 1 over R1 plus 1 over R2. And that's how we got this equation to calculate the effective resistance of parallel circuits. Now some of you might find that you have a different equation in your textbooks, and that's actually derived from this equation. So some of you may have seen this equation instead. So I'm going to write this over here. So given that 1 over R equals to 1 over R1 plus 1 over R2, so if you were to combine these two into the same fraction, you would end up getting the denominator of R1 times R2. So because R1 times R2 on top becomes 1 times R2, giving you R2. And for the second fraction, R2 times R1, so it becomes 1 times R1, so giving you R2 plus R1 over R2 times R2. Let me just fix that. And because it's 1 over R, you just need to invert the fraction, leaving you with R equals R1 times R2 divided by R1 plus R2. And that's an equation that some of you may have seen in your textbooks. Now personally, I don't really recommend the use of this fraction because this only works when you have two parallel branches. If you have three, suddenly this fraction doesn't work. And it's not as simple as just adding another R3 at the back. R1 times R2 times R3 over R1 plus R2 plus R3. That's not true. However, this fraction works because all you need to do is add the third fraction. That means 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. If there's more, keep adding plus 1 over R4 plus 1 over R5 and so on if you have multiple branches. So although this is in your textbook, my personal recommendation is to use this equation. Let me just move my cursor so that you can see it. Use a highlighted equation because that would work no matter how many branches you have. You need to remember that each fraction represents one line. If you have two lines, you must only have two fractions. If it's three lines, three fractions. Now it can get a bit more complicated when it comes to solving series and parallel circuits. So if I were to just backtrack to this comparison chart, it looks very straightforward, but the reality is that you do need to know how to interpret the series and parallel circuits correctly and when to use these equations for the comparison. If you have a more complex circuit which uses a combination of series and parallel connections, you can only use these comparisons for those sections. So for example, if you have only one part that's series, you can only use these comparisons for the series section. If you have another part that's only parallel and not the entire circuit, then you can only use these parallel comparisons for that section that's parallel. To understand this more, it's best if we go through some examples on how to solve various electrical circuit questions. Now I'll cover those examples in another video because there's so many different examples that we could go through. I'll do my best to find various examples and cover them in separate videos. So for now, that's all for this video lesson. So, if you found this video to be educational and helpful, do click like and let me know in the comments below how you have found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do watch my videos on other topics on my YouTube channel which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!